It's Mrs. Mafucci. Let's continue our discussion on the kinetic molecular theory of matter and the three phases of matter. We're going to begin with a look at the nature of liquids. So turn to your reading strategies and take notes on the right side. 13.2, the nature of liquids. How are liquids similar to gases? Gases can flow, liquids can flow. The individual particles can change positions. This is why both can take the shape of their containers. Gas particles have kinetic energy. Liquid particles have kinetic energy. Both gas particles and liquid particles are in constant motion. Well, how are liquids different from gases? The kinetic molecular theory assumes that there is no attraction between gas particles. We know that there is some attraction, but those attractive forces are very weak, so we pretty much ignore them. The particles in a liquid, however, do attract each other. These are referred to as IMF, or intermolecular forces of attraction. The intermolecular forces of attraction are much stronger for those in liquids than in gases. Because there are stronger IMFs in liquids, there is less space between the particles. Therefore, liquids are more dense than gases. Let's now consider evaporation. Vaporization is defined as when a liquid changes into a gas. Boiling is when vaporization occurs at the boiling point and takes place throughout the sample. Usually, it's accompanied by the formation of bubbles. Evaporation, on the other hand, is when vaporization occurs below the boiling point and it takes place only at the surface of a liquid. It is not accompanied by the formation of bubbles. As temperature increases, the rate of evaporation increases because more of the liquid particles have enough energy to escape those IMFs and become gases. As temperature decreases, the rate of evaporation decreases. When evaporation occurs, the particles with the highest kinetic energy at the surface of the liquid have enough energy to break those intermolecular forces of attraction that keep them in the liquid phase. These particles evaporate, leaving behind the liquid particles with lower kinetic energies. Therefore, as a liquid evaporates, the temperature of the remaining liquid decreases. If you look at this diagram, the particles at the surface of the liquid with enough energy are able to evaporate, leaving behind those particles with medium energy and lower energy. Now let's consider vapor pressure. What happens to evaporation when a lid is put over the container, creating a closed system? Well, the lid prevents the vapor from escaping, and instead the gas particles become trapped, colliding with the walls of the container, producing pressure. This pressure is known as vapor pressure. The pressure exerted by a gas above its liquid is called vapor pressure. The higher the temperature, the greater the vapor pressure. Why? When you place a lid over the container of a liquid, you create a closed system. A closed system can establish equilibrium. Equilibrium is when the rate of two opposing reactions become equal. In this example, the rate of evaporation becomes equal to the rate of condensation. Evaporation when a liquid becomes a gas, condensation when a gas becomes a liquid. Equilibrium is established when the rate of evaporation equals the rate of condensation. Let's look at boiling point. The boiling point of a liquid is the temperature at which the vapor pressure is equal to the atmospheric pressure. Atmospheric pressure is caused by the forces of the gases in the atmosphere pushing down on the Earth's surface. If the atmospheric pressure increases, the boiling point of a liquid increases. There's more forces pushing down on the liquid, decreasing the rate of evaporation, increasing the energy needed to change a liquid into a gas, and this is why the boiling point increases. If the atmospheric pressure decreases, it makes sense that the boiling point decreases, because the pressure exerted on the liquid by the atmosphere is low, which means it's easier for those liquid particles to change into a gas. Normal boiling point is defined as the boiling point temperature at standard pressure. The normal boiling point of water is 100 degrees Celsius. That's if the pressure is 1 atmosphere, 760 millimeters of mercury, 760 torr, or 101.3 kilopascals. Well, finally, let's look at the nature of solids. Solids are characterized by having a definite shape, a definite volume, strong intermolecular forces of attraction. Solids do not flow, even though the particles of a solid can vibrate in a fixed position. The particles of a solid do not change position. They're only vibrating. Solids have an orderly arrangement. The melting point of a solid is the temperature at which the kinetic energy of the solid is strong enough to break the IMF and the solid melts. The freezing point of a substance is the same as its melting point. The freezing point of water is 0 degrees Celsius. The melting point of ice is 0 degrees Celsius.